Next up in our stages of integrals and antiderivatives, we're going to be doing stuff called the average function and the mean theorem. I'm going to start with the average function just because that's the right order to do this in. First, we have the formula for the average function, which is f average is equal to 1 over b minus a times the integral of a to b, which is f of x dx, so just the derivative of some function. So I decided to give you guys an example here, and there's not really like a proof to this that we're doing. You're not finding proofs for this. This is just the function you're going to be using, and it's on your formula sheet. For our example here, we have f of x is equal to x squared minus 4x plus 5, so simple polynomial, and it's just an upwards parabola. And it says on 0 to 5, I should have squared this bracket, it's okay. But this doesn't mean that you're finding that point. These are actually the bounds that we're putting in for our a to b. So we have here that f average equals 1 over 5 to 0, because this is a and that's b. And then we have our integral from a to b, 0 to 5, of x squared minus 4x plus 5 dx, as we've been doing this whole time. Now to find the average function, you're just going to be factoring in and doing integrals as you have been this whole time. So we have the f average is equal to 1 over 5. You can keep this on the outside as long as you're multiplying by the whole function, times our antiderivative, which is x to the 3 over 3 minus 2x2 plus 5x. And remember to put this in notation at the bottom to show that we're still doing bounds from 0 to 5. Now moving on, we need to do the fundamental theorem of calculus, which is f of b minus f of a. So we have f at b, which is 5, minus f at a, which is 0. And we Now I'm going to be explaining the difference between a definite integral and the area under a curve. Here we have first the integral, and this graph is going to be for both integral and area, and this is just a polynomial with areas in the positive and the negative. The 5 and 10 are just numbers to show you that it does intersect with x and goes all the way through. But first, for the definite integrals, the notation that you could use is the area, the integral bounded from 0 to 5, of our function plus 5 to 10 of our function plus 10 to 15 of our function, because that's just finding this area under the curve for each. But you'll notice that part of it's in the negative. When you're finding a definite integral, you're just ignoring that part's in the negative because you're finding the net amount of your final number. And this can also be written as the integral from 0 to 15 of f of x dx. It's the exact same thing since you're disregarding the negative. There's no reason to expand it. In the area under the curve, you have to expand it in order to account for this negative here, because in the area, you want to find the total area under curve and the area above the curve here. So the first example, to make sure that you take account for that negative, is you have the area bounded from 0 to 5 of f of x dx. And normally you would just add, as we have been in the other ones, but since it's negative, we can subtract the negative and it'll create a positive number. And then you just add the last bit. Another way of doing this is to take the absolute value of the section that's going to be negative. This will take the negative number and turn it into a positive, so you'll get the positive area. And the last way is switching the bound. So you'll have your normal section for the first that's already positive, the integral from 0 to 5. Then for the middle section that's negative, you're just going to take the numbers and switch them around. So you notice here it's 5 to 10, but instead we do 10 to 5, and this is basically just changing it from negative into a positive like we had been in the other two examples. Now this is, the area is finding the gross, whereas the integral is finding the net. The net is just adding up all of the numbers together and taking that number and ignoring that there were any other negatives and positives. You're just finding your total, basically. But for the gross, you're changing all of your negatives into positives to make sure you have a final number that's completely positive. Next up, we're talking about something called the properties of integrals. And the properties of integrals is defining the notation that integrals can be written in and what that means for your function. So first of all, we have multiplication here. So if you have the integral of something, your function, multiplied by a constant on the inside of your integral, you can move the constant onto the outside of the integral, and this can make it simpler to factorize and find the antiderivatives of your function. You'll be working with smaller numbers, so you don't have to multiply anything in until the end. Next, we have the sum, and sum is when you have the integral of two functions inside, and you can separate them into two integrals or the other way around. So if you see something like a function that's separated into two integrals like this, for example, when you're finding area and stuff, which we'll be talking about, you can put it down into one if you like it like that, or you can separate it into two if it makes it easier. You can do the same thing with difference, except there's just a subtraction there instead. You have the integral of your two functions subtracted, and you can separate it into the integral of each individual function to make it easier to work with, or the other way around. If we're doing this bounded rational, we have the equation, the integral of 2 to 4 of 2 minus 8x divided by 8x to the 3 dx. I'm going to be using u substitution to do this, just because there'd be chains and product laws if I didn't. So we're setting u as 8x. du dx, so the derivative of u, is 8, and I isolate for dx to get du over 8. Now I can put in the integral of 2 to 4. Once we plug in u, we get 2 minus u divided by u to the 3 times du over 8. Since we put in the dx, we're at dx here. We learned in properties of integrals that we can take the multiplication of a constant and take it on the outside of our integral. So we have 1 over 8 on the inside of our integral, and I just moved it to the outside so it won't mess with all our equations on the inside. And now I can just cancel out this 1 and 3 in the bottom here and create 2 times u to the negative 3 minus u to the negative 2. And there's still a du because we need to find the antiderivative. I'm going to put a little 4 there because it's bounded from 2 to 4. Moving on, we found the antiderivative, and this means that capital F of x is equal to 1/8. Now our 1/8 is back in, but it's just on the outside of the parentheses, multiplied by negative u to the power of negative 2 plus u to the negative 1. And there was a 2 there, and it canceled out with the 2 that was there before. And the same thing with a 1. This turned into a positive because you divide by negative 1, and it was a negative before. And the two signs adjust to make a positive. And this is bounded from 2 to 4. And I just plugged in our 8x back in for u. So now we have 1 over 8 times negative 8x to the negative 2 plus 8x to the negative 1, bounded from 2 to 4. We can do our fundamental theorem of calculus at this point and put f at b minus f at a. So f at 4 minus f at 2, and I save you the time of writing these all down because they're really small numbers. And after you put in your calculator, it might give you a decimal, but you can actually turn it into a fraction using the frac thing. And you end up with the integral from 2 to 4 of f of x is equal to negative 29 divided by 8,192. Here's an example of a bounded polynomial now. We have f of x is equal to the integral of negative 8 to 2 of x squared plus 8x minus 9 dx. In order to find our antiderivative, we need to just do the simple opposite power law that we've been doing this whole time. So it's x to the 3 over 3 plus 4x squared minus 9x. And once again, remember to put your notation, so it's bounded from negative 8 to 2. Now we need to do the fundamental theorem of calculus, and it's f of b minus f of a. So we have f at 2 minus f at negative 8, and it's equal to negative 470 over 3. Now at the very end, you just want to write your final answer, so we know that the integral bounded from negative 8 to 2 of f of x dx is equal to negative 470 over 3.